The subject of this talk is designing multi-cluster applications, it was listed as part of the architecture track, but I would also call it part of the in-field war stories track. And when I talk a little bit about my background, I think you'll kind of see how I've accumulated these war stories. My name is Lucas Beeler. I am a professional services architect at GridGain. I'm at the GridGain headquarters in Silicon Valley in Foster City, California. I work in a post-sales role, which is to say I actually help our customers architect, build, deploy, and scale GridGain-based applications. I actually worked at Gigaspaces, another IMC vendor, in exactly the same role before I joined GridGain. As I mentioned, this presentation is the result of my own kind of hard-won experiences designing and building systems for my largest clients. One thing that I will say that is a little unorthodox is that, first of all, the approach I'm going to present may seem antithetical to a lot of the received wisdom that we have about in-memory data grid-based application design, right? We have kind of a whole culture around this notion of shared nothing architectures and trying to make every cluster node the same and do everything within a single cluster. And I'm going to kind of smash that and say that there are a lot of applications where you may actually wish to use multiple clusters and to make clusters themselves the building blocks of your application for separation of concerns, loose coupling, that kind of thing. The other thing that I'm going to try to do is I don't really want this to be a marketing or sales presentation for GridGain. So where possible, I am going to incorporate references to Gigaspaces, Hazelcast, Coherence, other data grids that I've worked with, because the ideas that I'm going to present are applicable to most modern in-memory data grids that support co-located processing. That is to say, your grid isn't just a dumb store for objects, it can also compute stuff. So as I say, I'd like to make this as platform neutral as possible. And the one final remark is that almost everything that I say about GridGain also applies to open source Apache Ignite. So moving on from who I am, let's talk briefly about what this talk is about. Well, as I mentioned, it's about building multi-cluster applications. So we're talking about single applications whose functionality is implemented over multiple in-memory data grid clusters. I just want to define some terms so we're all cool about their meanings. Insofar as I'm concerned, for the purposes of this talk, a cluster is a distributed in-memory data grid that supports co-located processing. So the co-located processing I cannot emphasize enough. If you look at Hazelcast, if you look at Gigaspaces, if you look at GridGain, and we'll get into how this works a little more later, all of those data grids support the idea of running code on top of data, right? The grid, if you think about it, all of the servers in your grid have CPUs, right? So in addition to being able to store objects, you have the capacity to run massively parallel compute operations, and that's the real power of these solutions. But we'll see that sometimes these solutions offer so much power that you can end up overloading the functionality of a single cluster node to the point where predicting scalability and behavior under load becomes very difficult. And I'm defining an application as a deployable set of code artifacts that deliver any kind of coherent, unified collection of business functions. And these artifacts are deployed and executed over a cluster or more than one cluster. Since we usually think about deploying code artifacts like jars to a cluster, for the purposes of this talk, we're actually going to be talking about deploying different code artifacts to different clusters with slightly different functionality And we do this for separation of concerns and orthogonal evolution and scalability. Now, orthogonal evolution and scalability, we probably have a pretty good idea of what those mean, but I'll actually define them as we get a little more into this talk. So the agenda for this session is basically, I'd like to just run through a conceptual overview of modern in-memory data grid functionalities. How many of you here are already working with an IMDG? Raise your hand. How many people are not working with an IMDG but are interested in them or are working with a traditional in-memory database like ×10? Raise your hand. Okay, so we've got kind of a mixed group, and I think it'll be good to run through the overview of modern IMDG functionalities. We're also going to discuss an example single cluster application and its limitations. We'll then discuss how we could transition that application to a multi-cluster design and the advantages of doing so. We're then going to see some case study implementations. These are systems that I actually built for my clients. And then at the end, we're going to have a question and answer session. We have quite a few slides to get through, so if you have a question, I'd love to take it. We're going to reserve at least 10 minutes for that. Please write it down, jot it down, and we can handle it at the end during the Q&A. So let's talk about the functions that a modern in-memory data grid might perform. So the first and most obvious one is in-memory caching of data in its native object form, right? This is what Tangasol did with Coherence nearly 20 years ago, and then Coherence was acquired by Oracle. And it has not just the advantage that data is kept in memory, because data can be kept in memory in a SQL database like MemSQL or something like that as well. But the biggest thing is that data is usually kept in an IMDG in its native object form. So for you guys coming from a Java background, those are actual POJOs. They may be serialized or marshaled to some extent, but they're POJOs, right? And you do not have to go through any ORM process from your client to stick something into an in-memory data grid. You just put an object. It's basically like a distributed hash table. And this no ORM idea was maybe even more important than in-memory when in-memory data grids first came into existence. There was a study done by eWeek or InfoWorld or one of the more prestigious industry trade publications back in 2013 that said that something like 20% of all CPU cycles in enterprise applications are spent doing object relational mapping. And if you think about frameworks like Hibernate that are very complex and rely on the Java reflection mechanism, you're burning a lot of CPU cycles there. So just the ability to kind of stick objects into a fault-tolerant grid where they were kept hot and live and in memory was a big deal. As time moved on, we started to add other functionality, right? And GridGain added SQL processing, right? And people started to do analytics like type classification, which is, something arrives in your grid, it's an object, well, what kind of thing is it exactly, right? Is it for example, if you have a notion of a customer, when a customer arrives in your grid, do you want to get an event that says, oh, a new customer instance was created, and then do you want to type classify that customer as a customer who is potentially a big spender and might spend a lot of money with your e-commerce site or your travel site, or someone who's only a casual user, right? Also, what happened was domain-specific performance analysis. So, in this case, performance is variable depending on your domain, right? In investment banking, it's probably how well did a trading strategy work. But in retail, it's something like how well did our recent marketing campaign work? So analytics were added, and then came stream data ingestion and ETL operations. So as data would arrive in the cluster, you wanted capabilities to change its form. GridGain, Hazelcast, Gigaspaces all support this, and ETL is a common use case for them. Later came event processing, which could be called reactive programming, or you could think of them similar to database triggers, right? If a price change event happens for a stock or a bond or a foreign currency, or if you have a customer hotel room booked or a booking object arrive, you need to react to that in some way to trigger some kind of downstream effect. People ultimately started using IMDGs to do things like provide a local mirror of SAS data, possibly in a different form, or push data to SaaS services. Another application is to integrate data from many sources into a unified queryable store. So, GridGain supports full ANSI 99 SQL. You can take data from a lot of different places. You can use the stream functionality to ETL that data into a common unified object model, hold it in the grid, and then access it in a uniform way. So IMDGs accomplish this range of tasks, which involve things like eventing, stream receiving, ETL, and compute operations by having functionality that goes well beyond just caching POJOs. I took this from our competitor Hazelcast, and you'll notice that, yeah, caching is here, but so is this whole notion of messaging, right? And what is implicit in messaging is that you have a notion of when a message arrives, you can react to it, you can transform it. I took this slide from documentation from Gigaspaces on their XAP in-memory computing platform. In this sense, you see a client invoke a service proxy. This is on a client server somewhere, and here we have 3 data servers. So in Gigaspaces, the places where you store data, the equivalent of like a table, is a space. So these little clouds are a space. But the point is that when you look at each of these server nodes, you're not simply seeing this space that holds data, you're also seeing services deployed there, right? And the point is that these services have the ability to actually execute data on top of, execute operations on top of the data stored in this space, right? So there's no data movement, right? This contrasts to a lot of architecture where storing something and processing it are very different, right? The most common example I could think of is that for that is something like you have an Oracle data warehouse and you have a Hadoop pipeline, right? And you do a massive SQL query out of your Oracle data warehouse. You run a series of MapReduce stages in your Hadoop pipeline, and then as a batch process, 8 hours later, you get some kind of result. Almost all of the IMDGs in use today allow you the ability to co-locate processing logic or services with the data that you're going to operate on. And this is one of the most powerful aspects of these solutions. From GridGain's marketing, I took several things. If you look at the way that GridGain is presented as a service, right, we of course have our data grid, right, which is a in-memory key value object store. We have compute grid, a massively parallel compute environment where you can broadcast or dispatch compute jobs out to nodes. Those compute tasks will then run on top of data on those nodes. We have service grid, the ability to deploy microservice endpoints within the grid. We have streaming, which is the ability to ingest streams from queues. We have receivers or sinks for things like Kafka, ActiveMQ. The point is that when you get this data in, you have the option to receive it, which can be an ETL or transforming operation. We've just added machine learning functionality. I just took this screenshot from the Apache Ignite website, and I took a Forrester Research review of GridGain in particular, and it says, oh, well, IMDGs in general suffer from a caching stereotype. Yep, I mean that's coherence. But GridGain smashes that stereotype by offering a general purpose compute grid. If you need an IMDG and a supercomputer all in one, then take a look at GridGain. This functionality is great, but it's actually not unique to GridGain, right? Other in-memory platforms do similar things. Let's now imagine, now that we've talked about this functionality, right? The fact that we can deploy services into a grid, right? The fact that we can run compute tasks in a grid. The fact that our grid can receive stream data via Kafka and we can transform it. Let's imagine an actual application. And let's talk about the pros and cons of this application and when it begins to break down. So let's imagine that we are a regional bank. We have 12 branch offices and 104,000 customers. And we do all of the things that commercial banks do. We take deposits. They could be checks, cash, electronic direct deposit, etc. We allow withdrawals through the similar mechanisms, including your debit card, which is generally processed by a processing network like Visa. We issue credit cards associated with a processing network like Visa or MasterCard. So you might have a Lloyd's TSB Visa card, for instance. We make loans. We manage relationships with our customers because we'd like them to engage with more of our products, right? If you have an auto loan and you have good credit, we'd like to offer you a mortgage. And finally, let's assume we're a US-based company, so we have to comply with relatively sophisticated state and federal banking regulations. So you guys have probably heard of the Dodd-Frank Act and Sarbanes-Oxley and all of these very sophisticated components of the US regulatory framework. So we want to build a system that will, based on an in-memory data grid for maximum performance, that will handle all of these business functions, right? And in fact, we can, and it's not even that difficult to build. I'd like to talk about some of the connections here. The core is our GridGain cluster, right? So this is a GridGain in-memory data grid cluster, but like GridGain, it's much more than a data grid. You can run compute tasks, you can run services, you can do stream ingestion. So let's imagine that we have data coming in from several different, what I would call ingestion actors. This is where we ingest data. So one of the most obvious ones is Visa, right? So we assume that our debit card is linked to the Visa processing network. So someone goes and swipes their debit card. That's a Visa transaction. We assume that the credit cards that we issue are also processed through Visa. ACH in the United States is the automated clearinghouse. They're the people that process checks. Believe it or not, I still have to write a check for my rent every month, which is obviously exorbitant because I live in Silicon Valley. And then there's Fedwire, which is the interbank network operated by the Federal Reserve that is used for bank-to-bank transfers. This is how I get paid every 2 weeks. GridGain's bank makes an electronic direct deposit to my bank. So we have events, if you will, coming in from all of these sources, right? There are customer transactions that could be deposits, withdrawals, etc. We also have query actors. We have terminals in our local bank branch if you want to go in and get some cash. And then we also have a notion of settlement processing, which is things may be held internally for a while, but then at 12 midnight, we may ultimately have to settle or resolve open transactions. We use a cloud-based CRM service. You could think of this as something like Salesforce or Zora, but the idea is it's a way of engaging with our customers. It allows us to handle marketing campaigns. If we find customers that match a certain criteria in our grid, and we think that, well, they're doing pretty well, and they just bought a Mercedes E-Class, we might want to hit them up for a, a home loan or something to that effect, right? So we have all of these components, and then one more, which is our audit database, which is required by Dodd-Frank and Sarbanes-Oxley, right? So let's just take a second and talk about, like, honestly how awesome this is, right? This is one of the great things about in-memory data grids before I kind of start hating on in-memory data grids. I mean, you know, we can do things like when a customer uses his or her ATM debit card to get cash at a foreign cash point, we can push a notification to our cloud CRM system here, and if that customer doesn't already have our SkyPoints Airline Rewards MasterCard, we can send him or her a spiffy marketing email that's like, would you like to earn Alaska Airlines and Emirates points? You know, every time you buy a latte. The system actually provides us with very rich primitives for building functionality. There's classes called Stream Receiver and Stream Transformer. You can check these out in the GridGain Java doc, but they're the principal instruments within GridGain for, say, receiving a Fed-wire transaction, which is actually going to come in a text format, and then you're going to have to convert it to something like a customer transaction POJO. So that's an ETL stage, right? We also have a wide range of compute, service, and event processing APIs to implement a business rules engine, right? And all of this happens because of the functionality offered by this grid right here. It's all of these things. It's data, it's compute, it's services, it's streaming. So this is great. I mean, I think we would all say, wow, compared to traditional architectures where you have to deal with multiple systems and your developers, who you pay a lot of money, have to deal with the cognitive weight of dealing with multiple systems, right? Like you might have to use Apache Spark in the past to do ETL stream transformation or something. You don't. And let's talk for a bit about how we implemented this pretty cool thing, which is we followed the best practices design protocols for clustered in-memory data grid applications. And those best practices protocols are based on this idea of shared nothing for maximum co-location. So the basic idea of shared nothing is that two cluster nodes do not have to share state in order to accomplish a business operation, right? If you think about it, the entire rationale for in-memory computing is that you don't have to do I/O. You don't have to do disk I/O, right? You know, memory is easily 1,000 times a disk, a random read from a modern SSD, right? However, if you have to use the network, you might as well be doing disk I/O. You're going to lose a lot of that performance. So hence, this whole notion of shared nothing and maximum co-location is the idea that all of our nodes are identical in configuration, and we can complete our entire business workflow within a single memory image. Now, the data may be sharded across our different cluster nodes, but for the data in a given cluster node, every business process on that data can be completed within a single memory image on that one node. So there is no shared state between nodes and no network movement is necessary. So for example, we can stream Fed-wire transaction receipts when I get my direct deposit here and it comes in to the same node where the final customer transaction POJO that corresponds to the transaction receipt will be stored, and then we can ETL them in place on that node from Fed-wire XML to a customer transaction POJO. So you can see Fed-wire messages being fed in parallel into all of these nodes, right? And that's fantastic because, you know, processing is distributed, right? I mean, you've got 12 cores here, 12 cores here, 12 cores here. They're all doing these ETL operations, right? You're taking advantage of that. At the same time, You know, nodes that are holding customer transaction instances of importance for marketing purposes can transform them directly into a REST JSON message and push that message out from their local memory images to our cloud-hosted SaaS CRM service. So what we might imagine is that, you know, you have a transaction come in to a cluster node, right? And it is not only ETL'd, but it's also classified as, well, this is a transaction that represents a specific type of customer behavior, and it's something that we would like to contact and engage with the customer more over. And we would then say, okay, let's push this out to our cloud CRM system. But so on every node, in order to do this in this shared nothing way, following best practices in IMDG design, we have customer transaction POJO instances. We've got the Fedwire stream receiver. We've got the Visa processing network stream receiver. We've got the ACH stream receiver. We've got a cache store adapter that can write data through or write data behind to our audit database. We've got a cloud CRM pusher service. We've got a query service that allows our branch terminals to access data if someone walks into a bank. And we've got our settlement processing query service. That's a lot of stuff to put on a node. But if you follow a shared nothing design where you try to do everything in a single memory image, that's what you get. And that's cool. But what happens at midnight Eastern time, which is the magic moment in all of US finance? Because that's where Fedwire and ACH transactions are sent to banks. At that point, these cluster nodes may become so saturated doing ETL operations that other pathways are unavailable, they may time out, or it might take a very long time. We're effectively experiencing resource starvation. And now we could do some very sophisticated thread management stuff in here. That is something that I've seen people do, right? Allocate certain threads to certain services, try to use thread affinity. But at the end of the day, as you guys probably know, working with threads a lot in an undisciplined or I'd say a way, unless you contemplate it very seriously, you can end up with very non-deterministic starvation behavior, right? So we'd prefer another way to do this, right? And, you know, so one thing we might do is say, oh, well, it's midnight, let's just add extra capacity. So we add another cluster node. This is the traditional scale out in in-memory data grids. But when we add this cluster node, what we're really interested in is just the Fedwire stream receiver and the ACH stream receiver. But yet we get holding customer transaction POJOs, the cloud CRM pusher service, and a branch terminal query service. And the other thing that has to happen is when you add a new cluster node in almost all in-memory data grids, data is elastically rebalanced. So there has to be data movement over the network from these 4 nodes to this new 5th node in an attempt to achieve a relatively uniform data distribution. So there's a better way, I think, and I've done it with a lot of my customers, and that's to leave shared nothing behind, right? You have multiple clusters that are physical or logical, and they're made up of different kinds of nodes. I call them subclusters. Shared nothing uniform provisioning still applies within a subcluster, but not between subclusters. And I'm going to be very upfront with you before I even talk about what we gain, which is down here at the bottom, about what we give up. DevOps isn't simple anymore. We don't just have one cluster node image to provision and send out. We have several. We can no longer scale the entire system by adding one node. Instead, we scale along different scaling axes. Each subcluster generally represents a different scaling axis. And we can't complete our business process without sharing data between nodes and performing network operations. Data has to move for us to complete our tasks. And so in that sense, we've broken shared nothing across the entire cluster. So you can do this, I mentioned, through physical or logical subclusters. A physical subcluster is an actual other cluster where that cluster holds a proxy to another subcluster. GridGain and other data grids support the notion of logical subclusters through something called cluster groups, where you can control deployment and say, I only want to deploy services or data on certain within a certain subset of nodes, and that becomes a logical subcluster. So the most obvious thing that I can think that we could do here would be to set up FedWire ACH receiver nodes in a special ingestion subcluster that is then separated from our data subcluster, and we separate that further from the cloud pusher subcluster. So requests come in, they are ETL'd here, and then the actual process of migrating this ETL data into the data node is a simple put, right? It's a virtually instantaneous cluster operation. Maybe you can even batch stuff up here and do a put all, which is a bulk operation and is even more performant. But all of that compute for ETL and the parsing of that XML is centralized here. Data nodes do not experience any query starvation. They will still meet their query SLAs regardless of how much data is coming in. I mean, how we do this in GridGain is pretty simple. GridGain, like almost every modern IMDG, uses declarative XML configuration, and we can attach user attributes to nodes. We can say, well, we have a node that has a role of fed ACH receiver, which is this node here, and we can only deploy those ETL services and stream receivers on those nodes. The immediate advantages are that, ETL operations are separated. Queries don't slow down when message volume is high. We can also bring down our ingestion subcluster and upgrade our FedWire and ACH ETL logic without affecting our data subcluster at all. The reason why that's often important is that oftentimes, upgrading logic that's deployed to nodes, because of the way that Java works, classes have to be reloaded from jars, and that means you have to bring the entire node down. So if we were to go back to this situation where our services and our data are all built into one node, we want to upgrade our service logic, this node comes down. Of course, all of the IMDGs are fault tolerant, so what happens, so what happens when that node, what happens when this node goes down is that data has to migrate to these other nodes, right? There are backup copies here, but if we set our replication SLA to be I always want to have 2 copies, then you have to start creating other copies in these nodes, right? So it is in this period, actually, of a topology change where data movement occurs, where IMDGs are most vulnerable, right? Your replication SLA may not be met. The intermediate topology state is where bad things tend to happen to good clusters. But if we're in a situation like this, these FedWire ACH receivers don't store any data. So you can bring them down and bounce them and bring them back up as much as you want. There's no data movement at all. The other thing is that we have both, in this sense, I'll first talk about this. This gives us the ability to do something called orthogonal evolution, right? Our FedWire ACH receiver logic, this code base can evolve entirely independently of the other code bases. Likewise, we then enter into the world of orthogonal scalability, where if it is midnight and we want to add more capacity, we just spin up another FedWire ACH receiver. We could spin up 2, we could spin up 4, it doesn't really matter. The data nodes remain unaffected, right? And because these nodes don't contain data, there's no issue of hydrating memory with data on disk or anything like that. Likewise, if we want to add more data capacity, we add a new data node and we don't really even worry about any of these other components. Orthogonal is obviously a mathematics term that we all learned in linear algebra about two axes that meet at a 90-degree angle. I think it's actually a really good way of describing it, right? I mean, you can scale along one axis without having any effect whatsoever on the other axis. There's no projection of anything on this axis, on the y-axis, onto the x-axis, right? And likewise, if we wanted to add a z-axis for the cloud pusher, we could do that. Okay, we just have a few more minutes here, so I'm going to move through the case studies relatively quickly. But before I do that, I am going to talk about some design themes in the case studies. So one of the things that you might all have heard of, it's kind of a hot topic right now in enterprise architecture. Martin Fowler wrote a blog post about it and very nicely let me use it in my slide. There's who here has heard of command query responsibility segregation, or CQRS, right? Basically, the way that data moves into a system can be based on an entirely separate data model from the way that data is queried from it. And you don't have to be a rocket scientist to see that if you have something like this, right, this is your command axis and this is your query axis. Multi-cluster designs are ideal ways of implementing CQRS architectures. And a lot of the, at least the two case studies we're going to bring up here, both take advantage of this. So case study 1, customer is a large wealth management firm. They've got about $1 trillion in assets under management. I'm sure all of you guys have a pension fund. It's managed by a wealth management firm so that your assets grow over time, and hopefully you retire in wealth and security. They actively trade in financial markets, and I built this system in conjunction with them where they had a very complex ingestion process, right? And this ingestion process, this is a service, which is a notion that we have in GridGain, and this is a continuous query, hence the arrow icon, which is another notion that we have in GridGain. You could think about it as an event processing engine. If you want reactive programming or to react to events, continuous query makes it sound like it works on polling, but it doesn't. It's event-based. But the point is you can have a query and you can say every time an object meets this query, I want to be notified about it. And the problem that the customer was facing is data would come in a very primitive and unenriched form. And it would have to be enriched in here. So the continuous query would pick up data in an unenriched state, a trading event or market change event, and it had to be enriched into something useful, because it was this basically just a control ID. And so we had to go out with a JDBC connection to this enrichment database. We had to do quite a bit of compute. And if this were a single cluster, these, and we had integrated our ingestion cluster and our data cluster, these data nodes would have slowed down. They would not have been able to serve their clients making web service calls in a timely fashion. And because what we are talking about here is an extremely low latency financial trading environment, the latency here was measured in microseconds. A second case study, we have a customer that's one of the largest fitness center operators in the US. They have about 300 gym clubs and 4 million members. They made a decision to move most of their customer engagement management and subscription management into the cloud through a very well-known cloud customer engagement management and subscription provider. They did that to lower costs. I mean, they'd much rather focus on improving the quality of their clubs, coming up with different subscriptions. But they had all of this data stored in the cloud, and the problem with putting something in the cloud is it may not be available. There may be network disruptions, there may be DDoS attacks. I mean, outages do happen even for Netflix and Gmail. And the other thing is that this SaaS provider had a very specific data model. It didn't agree with the customer's existing business objects model. So we basically set up a special cluster that acted as a sender-receiver hub between the cloud-based SaaS provider and the client's on-premise data store. And it effectively does a fetch and reconciliation operation every 15 minutes. And in that sense, the client maintains a constant local mirror of data in the cloud. Finally, to say the themes of these case studies, in both cases, interacting with external systems was critical. And in this case, the time required to communicate with those external systems, say the WAN link to the cloud SaaS provider, dwarfed any time costs associated with local data movement between nodes. So yes, we broke a shared nothing design, but it didn't matter, because the time cost of hitting any kind of thing over a WAN is maybe 1/1000th of moving data over a 25 gigabit Ethernet interconnect or a fiber channel backplane within the same data center, right? In another case, compute-intensive ETL operations were required, and the time to complete these operations were several orders of magnitude greater than network movement time. So I would say that these are scenarios where multi-cluster designs really start to make sense. Whenever you have operations that have to be performed that would dwarf the network transfer time between nodes, which, by the way, is getting smaller and smaller, so these designs are becoming more applicable, it's something you might want to think about. And when thinking about this at the end, I wanted to just put together this curve based on my understanding working with customers for many years in in-memory data grids about a capability maturity model for in-memory computing. I think people start out caching objects and basically just fronting a database with POJOs, right? And they do this for a lack of ORM, for speed, and for scalability by adding other nodes. Ultimately, you come to co-located computation and this sort of running code and services on top of data. That's fantastic, right? Most people do this in a shared nothing way. Ultimately, however, you'll find that this becomes difficult to maintain. And so things like separation of concern, orthogonal evolution, orthogonal scalability become really important. So I'd say I see my most sophisticated customers using multi-cluster designs now for their largest systems.